after 2 weeks not seeing statistic, I don't know if you review a bit at home, but let's review what we have done for hypothesis testing. 3 weeks ago, we did hypothesis testing on mu, consists of 6 parts: claim, hypothesis, test statistic, p-value, informal conclusion, and then conclusion. If we are testing on mu with sigma known, then we use the test statistic is C because we know the sigma. Then 2 weeks ago, when we did hypothesis testing for mu with sigma unknown, then because the sigma is unknown, then we substitute this sigma by S. We substitute population standard deviation by sample standard deviation. Now, for that reason, then, the test statistic change becomes T. But computation-wise, it's still the same, okay? Now, but because we use T distribution, then originally the p-value is supposed to be normal CDF. Now it becomes T CDF. Now, also 2 weeks ago, we also apply hypothesis testing on P, on population proportion. Then what will the modification be? The modification will be, of course, we are not testing the mu anymore. We are testing the P, right? We test the P. Now then, what is the test statistic? The test statistic will stay as using Z, yet the formula change becomes this. You can think of that as the following modification. Maybe I use slightly different color. Maybe this one, this one here. So the X bar was replaced by P hat. Okay, and then the sigma is replaced by PQ. Okay, the sigma is replaced by square root of PQ. And the rest, the p-value, of course, stays with the normal CDF. That's what we have from 2 weeks ago. And sure, you can review that from the lecture 2 weeks ago. Now, what we will do today, the part from our chapter 9, is it chapter 9 or chapter 8? I don't remember. Let me go look back. Give me a second. Yeah, chapter 8. So from chapter 8, the one missing is hypothesis testing on sigma squared population variance or population standard deviation. Now, the modification will be, why my line cannot be straight? The modification will now be on, of course, step 2. On step 2 and step 3 and step 4. Step 2, the hypothesis. We will be testing not the mu, not the p, but the sigma squared or sigma. So it's either sigma squared equal to, less than equal to, greater equal to a constant, as opposed to not equals to, greater than, less than a constant. Okay, but a little modification further, it is possible. It is possible what we are testing is the population standard deviation instead. So instead of sigma squared, we get sigma. Okay, depends on the claim. Is it about population variance or population standard deviation? The next modification besides step 2, step 3, the test statistic. Just like in confidence interval, when we did confidence interval for variance or population standard deviation, we use chi-square, right? Then the test statistic here will also be chi-square. The formula is the degree of freedom times sample variance over population variance. That's the formula. Now, in confidence interval case, the lower bound and upper bound were this one. Chi-squared is between degree of freedom sample variance over chi-squared right, and n-1 sample variance over chi-squared left. Now, you can see if I modify from either two of these sides here, we can, let's say this is equal to, right? Now multiply by chi-square both sides and then divide by sigma square both sides. We get the formula we use here. That's how we get that formula. Okay, I mean, maybe that's not how we get the formula, but that's how they are related. Okay, to enable you to memorize that better. Now, step 4, of course, when we do the p-value, we cannot use normal CDF nor t-CDF anymore. We will use chi-square CDF. Okay, that's the p-value. Yeah, chi-square PDF, chi-square CDF equals to lower bound, upper bound, degree of freedom. Now, that's what the structure be. Now, of course, we will need to apply this to examples. Let me find the examples. Give me a second. I believe you can find these examples from hypothesis testing procedure 2. The handout I gave you 2 weeks ago in the later part. Let's see. I will, from your handout, I will use example or problem number 7. I'll use problem number 7 as an example. This is from handout 2. Hypothesis testing procedure 2. Give me a second. My daughter and my son is playing next to me, so they keep on calling me. Okay, let's start. So what we have here is the observed variance for the 100 measurements of gear diameter is that. So what we know is that the n is 100. There are 100 measurements, and the sample variance, the observed variance of this 100 measurement is 0.00003969. And I give the comment there that the standard deviation is 0.0063. That's because if the sample variance is that, then the square root, which is the sample standard deviation, is the square root of that number, which is 0.0063. Okay, now sometimes they give you the sample variance. Most of the time, the question gives you sample standard deviation. Okay, now the question is test if the true variance is equal to 0.01. That's our claim. Claim the true variance, of course this refers to population variance, of measurements, or actually of gear diameters, is 0.01. Okay, of course what we would like is when we produce something, then as we would like the variation to be as small as possible. Now, the variance of the product we have represent the consistency of what we make. Okay, so the larger the variance, then the less consistency of what we do, of what we produce. Hypothesis. Hypothesis, then the null hypothesis, alternate hypothesis. Variance is 0.01. Oh, okay, so population variance is 0.01 because it has equal sign, then it goes to the null hypothesis. That's the claim. Now, then the alternate hypothesis is sigma squared is not equal to 0.01, and then we know that this is true tail test. Step 3, test statistic. Test statistic chi-squared equals to degree of freedom 99 times sample variance 0.00003969. You can also use, of course, 0.0063 being squared. Okay, depends on what the number you use there, but you keep in mind that that place is for sample variance, not for sample standard deviation. If you, right now, I have the sample variance, right? So I will just use the sample variance as is. But if I don't have the sample variance, then I use sample standard deviation, right? But the standard deviation should be squared to get sample variance. Now, the denominator is the sigma squared, which is from the constant of the null hypothesis, that's 0.01. Now then we use our calculator. 99 times 0.00003969 divided by 0.01. That's 0.3929 93. That's step 3. Step 4, the p-value. Let me do it on the right hand side here. P-value chi-square distribution looks like this. It's non-negative and skewed to the right. Okay. Now, because this is a two-tailed test, then I need to find the area. Okay. The peak here is equal to the degree of freedom. I'm not really clear if it is equal to degree of freedom or the sample size precisely. I don't remember. But we know that the sample size of degree of freedom is approximately 99 or 100, right? So 0.39293 must be on the left-hand side. Must be on the left-hand side. 0.39293. Now then I need to find the area of the tail and then double it. Okay, so the p-value is 2 times chi-squared CDF. Lower bound is 0. Remember that chi-square distribution is non-negative, right? So it starts from 0 on the lower bound. The upper bound 0.39293, degree freedom 99. Okay, now let's get our calculator. A second. How to punch that calculator in. And we go to distribution and scroll down to chi-squared CDF. The lower bound is 0. Actually, somebody asked me this question, Thomas, what if I use the lower bound negative E99? It will be okay because to the left of these, to the left of this number here, it's all 0. So even if you start from negative infinity, right? Our calculator will consider the area to the left of 0 as 0. So yes, you can use negative E99 here. You will get the same result. But I just wonder why. You know that to the left of 0, the area will be 0. So why do you want to count it, right? Okay. So no need. Just use 0. Just use 0. But if you use E90, negative E99, you will be okay. That's what I'm saying. Okay, so the lower bound is 0. The upper bound is 0.39293. And then degree of freedom is 99. You'll get, well, that's 0. The area is so small that it's basically 0. So the p-value will be 0. Then step 5, informal conclusion. They don't tell us what's the significance level. And therefore, we assume that's 5%. But even if you make it 1%, you still come up to the same conclusion, that is reject null hypothesis. Right? Okay. Which happens to be the place where we have the claim. So in our step 6 conclusion, then the wording will be trying to refute the claim, okay, reject the claim, trying to reject the claim, and we have sufficient evidence for that, okay? There is sufficient evidence reject the claim. That the true variance of gear diameter is 0.01. In fact, if I change the wording a bit, I change the claim to be the true variance of the gear diameter is less than 0.01, then we will support that claim because, well, the p-value of that left tail is already 0. Okay, so it's definitely not 0.01. It's definitely much less than that. Okay, now that's for this example. Oops, go back here. Now I would like you to try one other example. I think instead of like doing a lot of examples, I prefer you to really understand what the examples you're working on, okay? And with the experience you have, I hope that you practice at home with the structures, then you should be good enough to do these problems with modification. Manufacturer of heart safety hats has designed the helmet so that the mean force transmitted by the helmet to the workers is 800 pounds or less, with standard deviation less than 400 pounds. Now, tests were run on a random sample of 40 helmets, so that's our sample size. The sample mean and standard deviation were, the sample mean is 825 pounds, and sample standard deviation 48.5 pounds. Now the question is, do the data provide sufficient evidence at alpha equals to 0.05 to conclude that population standard deviation of the population standard deviation of the force transmitted to helmet exceed 40 pounds. They want that to be less than 40 pounds, but the test here is to test exceed 40 pounds. Okay, so basically they want to test if the population standard deviation is more than 40 pounds. Okay, then let's do the claim. The claim, the population standard deviation of force transmitted by the helmets to the workers is actually exceeds 40 pounds. And if that's the case, it means their design, that's what they try to design. Their design, they want to have standard deviation less than 40, right? Now they suspect that because of this random sample of 40 helmets come up with this number, then they suspect that their design is flawed. Then how do we check that? Then we see in the hypothesis, null hypothesis, alternate hypothesis. The test here is on population standard deviation. So that's sigma, not sigma squared. That's sigma greater than 40, which is the claim. And therefore, that's a right tail. Do you remember why we call that right tail? Because it's greater than a constant. If it is greater than a constant, then you need to come up to come up to a test statistic strictly greater than a certain number. Okay? It's greater than means the tail will be going to the right. Therefore, test step number 3. Can I ask you to do this? Start from here. The formula is chi squared equals to n minus 1 s squared over sigma squared. So let me ask you to do this step 3 and 4 and 5 and 6. So to complete that, 1 minute, another 1 minute, another 1 minute, 2 minutes. So 5 minutes from now, let's say 8:55. Okay, go do it.